And today we have Finn telling us about wild P structures. Take it away.
Hey everyone, well, thanks for having me. So in particular, I'd like to thank Vaki and Sam for organizing this. And so as Vaki has said, I'm going to be talking about wild P structures. So just to give some overview, I'd like you to consider a relatable question, which is the question of whether to P or not to P. So, I mean, what do I mean by this? I'd like to illustrate it in the case of kind of a thesis scenario. So suppose you're a graduate student living in a pandemic, and you log onto the Zoom call with your advisor, and you've reached a stage in your graduate career where you're kind of ready for a thesis problem. So you sit down with your advisor, they look you in the eye, you say, I'm ready. They tell you think you're ready, and this is what they say. So they say, okay, take P greater than 2 to be a prime and a positive integer. The question is, can you classify the finite subgroups of GLNC such that the order of G is the power of P? They say, okay, my method, you should study 2 cases. There you go, Zoom call ends, and you're left with this problem. So some of the point of this talk is that I'd like to kind of convince you that this is really one of these kind of red pill versus blue pill scenarios. So you should expect the case when P divides this integer n to be significantly more complicated than the case when P is co-prime to n. And so I'll give you some kind of moral explanation for this. This is really just an excuse to introduce some terminology. So when P divides n, we'd say that the P local structure of a group like GLNC has a kind of wild or red pill aspect to it. Whereas if you study the case when P does not divide n, then the P local structure of GLNC is so-called strictly tame or kind of like a blue pill. Okay, so what I've been describing here is something which is kind of meant to be represented by this box. So it'd be called kind of P local subgroup structure of something like GLNC when P divides n. And so one of the talk is to kind of give you some examples in this circle of ideas. So this wild P local structure over here, it turns out, is actually closely related to another wild P local structure, which is the degree D polynomials over QP when P divides D. So I will define QP and I'll give you some examples in this box over here. And similarly, you can study wild P local structures in representation theory. So I'm not going to say anything about reductive algebraic groups, but I will describe a little bit here. So we're just going to see some examples here, but we're going to start quite basic, and we're going to talk about the real numbers. So I'd like to give you kind of maybe a bit of a sophisticated point of view on the real numbers. So I like to think of real numbers as kind of being represented by Cauchy sequences. So for me, a real number is just a Cauchy sequence of rational numbers taken up to equivalence. And okay, when you say Cauchy, you have to specify which metric you're working with. So we just use the standard metric on the rational numbers, right? You take the difference of the absolute values, that's a metric. This isn't quite how you would usually study real numbers. So usually when people teach you about real numbers, they write down things like this, right? They say, okay, we're going to take some positive integer n or greater than 2, and usually it's 10. And then they talk about so-called n-simal expansions, right, which is just strings of digits between 0 and n minus 1. And they say that's a real number. Okay, well, how does it connect back to this business with the Cauchy sequences? Well, okay, you write down some power series using your digits. Power series is really a sequence of partial sums. The sequence of partial sums is a Cauchy sequence. And the metric on the rational numbers is such that this Cauchy sequence is always convergent, irrespective of how you choose n. So one nice property of this description is it shows that there's really no there's no kind of canonical way of picking n, right? We have 10 fingers. That's why we typically choose n to be 10. But we can talk about real arithmetic in this setting. So for example, if you want to add 2 real numbers, if you're thinking of them as Cauchy sequences, the addition law is you just take pointwise addition on the entries in the Cauchy sequence. And the multiplication is just pointwise multiplication of the entries in the Cauchy sequence. So right, there's something to check here, which is if you multiply 2 Cauchy sequences, you get a Cauchy sequence. That works out essentially because the absolute value on the rational numbers is submultiplicative. So it's actually multiplicative, but you only need the submultiplicativity here. And okay, you can translate this into what happens with the power series. You get some rather complicated looking formulas for multiplying power series. is perhaps not something you've seen, but I claim that you've really seen this in the case when the expressions are finite. So in grade school, they teach you how to multiply ensembles using these things called carry operations. And so I'd like to kind of review the carry operations because I think they're quite important for the p-adic numbers. So let's just see some examples of carry operations in action. And if we're going to work base 5, okay? So we're going to do some carry operations base 5. I want to add these two real numbers. These are mod 5. So what I do is I start at the right and I do my addition. So I do 2 plus 3 and take the remainder mod 5. So that's a 0, and I carry the 1. And then I do 1 plus 4, take the remainder mod 5, carry the 1. Now I get a 1, carry a 1. Now I get a 2, carry a 1, and so forth. You can also do multiplication of real numbers. So you take 2 times 4, that's an 8, which is a 3 mod 5. Carry a 1, 2 times 2 plus 1, that's a 3. Don't have to carry. 2 times 3, that's 6. That's a 1 mod 5. Okay, now you move to the next thing. Drop a decimal point. This one's kind of fun. You do 4 times 4, that's a 16, which is a 1 mod 5. And this time you carry a 3. And okay, hopefully you get the idea. This should be kind of familiar to you. All right, it's this kind of neat algorithmic way of multiplying ensembles. So now you just add up these numbers and you have carry operations for that, so it's all good. It's pretty nice, but it's only really nice because you're actually multiplying rational numbers, right? So on finite ensembles, these are really just rational numbers. And I'd like to draw your attention to the fact that kind of true irrational arithmetic is a little bit less nice. So for example, if I just give you 2 infinite strings of digits and say, tell me the product, well, you're going to go to the right and you're going to start doing carry operations, except the trouble is that these things go infinitely far to the right. So you need to truncate. All right, so a little example, right? If you want to compute the first 10 digits of pi times e base 10, you actually need to approximate them both to 12 digits and do the calculation if you want to get the right decimal point at the end. Okay, so that's kind of maybe a minor issue with R. The other issue with R is that it's quite boring. So in the sense that arithmetic over R is not particularly interesting, right? If I give you a polynomial over R, then you can split it into linear factors, assuming you're willing to kind of accept the existence of the square root minus 1. So it turns out that once you adjoin square root minus 1, you can solve all polynomials. And the Galois group is as simple as it could possibly be. It's just a Z mod 2Z. So here's just a little summary of how I feel about real arithmetic. And we're going to fix this. So right, I did actually like this carry operation stuff. This was kind of neat. So I'd like to somehow recover the carry operations, but get something which is a little bit more interesting. And so my idea is that I'm just going to flip everything. So I'm going to introduce this object backwards R, which is just temporary notation. And what I want this to be is I want it to be some arithmetic structure where a calculation like this works. So say I want to add these things mod 5. Well, okay, I want to multiply them actually. So I do 3 times 2, that's a 1 mod 5, carry a 1, but now I carry in the opposite direction. Now I do a 3 times 2, that's a 6, add 1, I get a 2, carry a 1. Okay, and so you see, I'm interested in 3 digits, and I'm only going to calculate things to 3 digits. So now I'm going to move to the next entry, drop a decimal, 1 times 2, that's a 2. 1 times 2 again is a 2, drop the 3s. 4 times 2, that's 8, which is the 3. And okay, now I add them up. Again, I carry from left to right, and it works out. You can see I got the first 3 decimal points, but I never had to worry about this issue of kind of truncating and then going further than I was interested in. Just by reversing the direction of the carry operations, it turned out that the calculation was kind of much nicer. So I want to investigate this a little bit. Oh yeah. So you have to make some concessions there, right? So if I want to add 1 and 4.44444 now, right, I get 1 plus 4, which is a 0, so I carry a 1. Then I get 1 plus 4, which is a 0, and I carry a 1. I get 1 plus 4, it's a 0, I carry a 1. I end up having the minus 1 is 4.444 recurring. So what I'm going to do is I'm just going to throw out the negative decimals. I mean, that's okay. And I end up with this thing. So let's just formalize this a little bit. So I fix some n greater than 2, and I'm going to define some arithmetic structure, which is going to be just like R. The elements will be ensembles like this, except the arithmetic is defined by reversing the base n carry operations. So this might seem like a little bit of a pedantic point, but now these n's on the right-hand side here, right? So I'm a little bit worried that the thing I'm defining might actually depend on n. You know, that seems a little counterintuitive. So I'm just going to put qn there. So just to make sure that I'm not accidentally, you know, forgetting to put the n dependence into the notation. And I'd like to ask some questions about qn. So the questions I'd like to ask are the following. Is there some way that I can represent these n-simal expansions in qn by rational power series such that the arithmetic in qn is given by algebraic power series operations? That's the first question. And the second question is, okay, is there a metric on Q such that these like formal rational power series I've written down are actually Cauchy relative to this metric? And so it turns out the answer to both of these questions is yes. So if I give you an n-simal in here, if you represent it by a power series like this, the key difference now is that the powers on n are increasing, then this reversal of carry operations will correspond to algebraic power series multiplication. So that's what I've said here. And okay, now you have increasing powers of n in your power series, so you might worry that it's not going to be Cauchy, but there is actually a metric you can put on the rational numbers such that this thing is a Cauchy sequence. It's called the n-adic metric. And how is it defined? Well, okay, the n-adic metric between two numbers, a and b, is the n-adic absolute value of their difference. To tell you what the n-adic absolute value is, so this thing is now some legitimately submultiplicative absolute value, which is defined in the following way. So you give me some x in the rational numbers. And it turns out there's a unique way of writing x in the form n raised to the power of some integer times a over b, where a and b are coprime, the denominator is coprime to n, and the numerator is not divisible by n. So you can do that. You can form these decompositions, and then you just declare the n-adic absolute value of x to be n to the minus L. Okay. So once you have these two things working for you, you can realize Qn in kind of the same way you realized R. So you can realize the n-adic numbers is actually just Cauchy sequences of rational numbers, where now your Cauchiness is taken relative to this n-adic metric. And you can realize the arithmetic on Qn by just, you know, the addition and multiplication of Cauchy sequences. So one difference I'll point out is that unlike in the case of R, you have n featuring here in this kind of intrinsic description of Qn. So you might ask, okay, how seriously do the arithmetic properties of this thing actually depend on Qn? Like, is this a good way of understanding it, or maybe there's some way I can actually drop the n? And so I'll just show you an example here of what can happen. So if we consider Q10, we can get zero divisors. So we can find non-zero elements in Q10, which multiply together to give you 0. I've written down an example here. So I take these two Cauchy sequences of rational numbers. So here alpha n is 6 to the 5 to the n, and beta n is 5 to the 2 to the n. And you have to prove that these things are Cauchy relative to the 10-adic metric. So that's a little difficult, and I'm not going to do it here. But we can see what happens when we multiply them. So when we do a times b, the nth entry is gamma n, which is alpha n times beta n. So that's 6 to the 5 to the n times 5 to the 2 to the n. You can do some rearranging, split up the 6 as 2 times 3. You get a 10 out the front. And then you get integer, which is not divisible by 10. So if you use your formula for the 10-adic absolute value, you actually find that the 10-adic absolute value of gamma n is 10 to the minus 2n. So there's a 2n here. And so I negated it. And so this is converging to 0 in the metric space Q relative to the 10-adic metric. So that tells you that a times b is 0. And so I'll point something out here, just to show you this 10-adic absolute value is a little weird. So, right, if you think about what the 10-adic absolute value of 6 to the 5 to the n, it's actually 1, right? Because this is an integer which is not divisible by 10. But if you reciprocate alpha n, the 10-adic absolute value blows up on you. So it becomes 10 to the 5 to the n. So this is because of the fact that when I defined the 10-adic absolute value, I said you have to clear divisors of 10 from the denominators of your rational numbers. So somehow you have to clear the factor of 2 to the 5 to the n, and you get a 10 to the 5 to the n. So that's nice. And what's also nice is that when P is prime, this thing is a field. So in the sense that you have, go for it.
So the previous slide, you said that multiplication is pointwise.
Mm-hmm.
So that means the alpha blah, blah, blahs aren't what you would use in the power series.
That's right, yeah.
Okay.
They're the partial sum ends, or the partial sums. So you take the.
Okay, right.
Perfect. Okay. So, right, we have this fact that when P is prime, QP is a field. I'm not going to go through the proof here, but I'll just say that the key property is that when P is prime, this p-adic absolute value is actually legitimately multiplicative. So it's not just submultiplicative. And so what that means is that if you want to prove QP is a field, you just write down the proof that R is a field, and then you put sub P's on all your absolute value symbols. So it's totally formal. It's just the same proof works in the case of the p-adic numbers, but the important property is that you have multiplicativity of the absolute value. Okay, so that's an example of kind of a formal similarity between R and QP, but there are a lot of other similarities. Well, okay, there are some very major differences. So it turns out that QP is arithmetically very much more interesting than R. So for example, if you consider the absolute Galois group of QP, then this is an infinite non-abelian group. I say here it's something we will likely never understand. So I don't know what we will and won't understand, but certainly we'll never understand it to the extent that we understand the absolute Galois group of R. So I'd just like to illustrate kind of some of the complexity that comes up here. So if we consider the field Q2, right? So we take P is equal to 2. We can ask ourselves, okay, how many degree D extensions are there up to isomorphism of Q2? So this is essentially a question about how many irreducible degree D polynomials are there over Q2 up to some notion of equivalence. And so it turns out that there's a lot of them, right? So if you take D is equal to 2, you get 7 isomorphism classes of degree 2 extensions of Q2. So that's already a lot compared to the real numbers, right? In the real numbers, you have 1 isomorphism class of degree 2 extensions. It's just the complex numbers, okay? But then, okay, if you go to the case when D is equal to 4, you have 59 isomorphism classes of degree 4 extensions of Q2. So that's like a lot of irreducible quartics over this field Q2. Then you go up to 8, you have 1,823. And when we get to 16, the reference I was using doesn't know what 16 is. That's probably not because of the fact that we can't compute this number, right? This data is coming from this thing called the database of local fields. So they actually have quite more refined information about this question. So I'll just kind of try to explain a little bit about what they do. So what they do is they take advantage of this surjective map of sets. So you can consider the set of degree D irreducible polynomials over Q2. And I claim that this set maps to the set of isomorphism classes of degree D extensions of Q2. So how do you build a map? You take a degree D irreducible polynomial over Q2, and then you take some root of that irreducible polynomial in the algebraic closure of Q2, right? So the algebraic closure is like the thing where all polynomials have roots. So you can always find roots of polynomials over Q2 in Q2 bar, okay? And then you just adjoin this root to Q2. So this will give you some degree D extension of Q2, and its isomorphism class will be independent of the choice of theta. So you have a map like this. And so what the authors who produced this database do is they give a set of polynomials representing the fibers of this map. So what does that mean? It means they describe a subset of the left-hand side such that if you restrict the map to that subset, it becomes a bijection. So they basically give you a set of representatives for polynomials which represent the different isomorphism classes of degree D extensions. So they actually write down the polynomials. That's the point I'm trying to make. And using these polynomials, they can get quite refined information about arithmetic of Q2. So for example, they don't just know the numbers ND. They can actually tell you what the Galois groups of the corresponding extensions are. So this is pretty nice, but you can see it's quite limited. Like they can't do 16 or 24 because these numbers are just too divisible by 2. There are some limitations though. So this type of analysis, it seems like it would become very difficult when the degree becomes very divisible by P. So when D is, divisible by 2 to the 4th, they can't do it. And it also doesn't give you all the information you'd like to know. So for example, it doesn't tell you how the various different subfields of QP bar kind of sit inside of each other. But it just tells you kind of representatives for the isomorphism classes, but it doesn't tell you about the subfield lattice. And it also doesn't tell you how many fields there are in a given isomorphism class. So if I fix some isomorphism class of extensions and ask you, okay, how many subfields of QP bar are there which are isomorphic to my fixed field? They're not able to really tell you about that. So this actually turns out to be pretty like hectic. So let me give you an example of the type of thing that can happen. So this is going to be our first example of a wild P structure. And what it is it's, I'm going to show you the P to the n degree, P to the n extensions of QP corresponding to the P to the nth roots of P in QP. Okay, so what I'm going to do is I'm going to fix a pth root of P in QP bar. And I'm going to form field extensions of QP by adjoining pth roots of P to QP. So the claim is that if I individually adjoin the P to the n distinct roots of the polynomial x to the P to the n minus P to QP, then that's going to give me P to the n distinct subfields of QP bar. And so these subfields are all going to be isomorphic to one another, and they're all going to have degree P to the n over QP. So what does it look like? So you take QP and you adjoin the pth roots of P. So these are the pth roots of P. So here zeta 1 is a pth root of unity. So if I take zeta 1 times the pth root of P and raise it to the P, I get P. And there are P pth roots of P, and they yield P different extensions of QP. Okay. And then I can go again. So I can fix a pth root of zeta 1 times the pth root of P. And then I can scale that by my pth roots of unity. And in doing so, I'll produce an additional P extensions of this field, each of degree P. And so altogether, I'm going to get P squared extensions corresponding to adjoining the P squared roots of P to QP. Okay, so this is a wild P structure, right? And in fact, this subfield structure will be reflected in the kind of subgroup structure of this, the subgroup lattice of this group, Galois group of QP bar QP. So this is really the invariant that we're going to be interested in. So the subgroup structure of this thing is going to encode most of what we'd like to know about p-adic arithmetic. So for example, these numbers ND, I can recover these just by understanding the number of different isomorphism classes of index D subgroups of this thing. So it's going to give me the numbers, but it also tells me about kind of the subfield lattice and the number of different subfields in any given isomorphism class. So the issue with studying this thing is that it's defined in terms of QP bar. So somehow QP bar is the thing I'm really struggling to understand. And I claim that, okay, it's enough for me to understand the Galois group, but well, the Galois group is defined in terms of QP bar. So it's difficult to kind of conceive of how you could actually get to the Galois group without first understanding everything there is to know about QP bar.
Question?
Yep.
So on the previous slide, why is it important that we take the pth root of P and not the pth root of any other number?
Why is it important we take the pth root of P? So it's to do with the fact that P, if you take like x to the P minus P, it's an Eisenstein polynomial. So, right, it's x to the P minus P is irreducible over ZP because it's Eisenstein, and therefore it's irreducible over the field of fractions by Gauss's lemma, and okay, I think that's the answer. I'm not sure. All right. Okay, so what I was going to say is that there is a way to actually study this Galois group without actually understanding the field QP bar. So it turns out that if you can understand the representation theory of GLN QP, then this gives you some way of actually studying the Galois group, which is going to bypass having to study QP bar or QP directly. So representations of GLN QP, these are homomorphisms from GLN QP into GLV, where V is some vector space, and GLN QP is just a set of n by n invertible matrices over QP. Excuse me. So everything I'm about to say in the remainder of the talk is going to be some approximation of what's actually true, right? So I'm not really going to be telling you facts here, but I'm going to give you kind of a zoom for thought version of the local Langlands correspondence. So this is the thing which allows you to do this. So what it says is that there's some kind of canonical bijection between two sets. Okay, so what are the sets? So one of the sets is the set of irreducible complex representations of this group GLNQP. Okay, that's a set. And the other set is the set of homomorphisms from gal E over QP into GLNC, where E is some finite Galois extension of QP. So here the field E will depend on pi, right? So you take an irreducible complex representation pi, it's one of these homomorphisms, and there's a pi on the E here because E might depend on pi. Right, so kind of maybe a little bit cleaner way of thinking about it is you can think of the irreducible representations of this group as somehow parametrizing homomorphisms from this absolute Galois group into GLNC. So that might be a more natural way of thinking about it if you're coming from this point of view. So right, the idea is to kind of illustrate some examples in this area, but I'm kind of interested in understanding the wild p-local arithmetic. So I mean that by that I want to understand degree D extensions of QP in the case when D is divisible by P, okay? And if I just stare at this formula up here, it's not really telling me how to single out the degree D extensions when D is divisible by P. So you might ask, okay, is there some way that I can use the representation theory to probe this particular type of arithmetic over QP? And it turns out that there is a way. So there is a representation theoretic way of distinguishing the representations, which will parameterize the wild p-local extensions via the local Langlands correspondence. And the concept to use is something called positive depth. So
I have a quick question on the last slide.
Yep, go for it.
Okay, so, all right, will you go back a slide for me? Okay, so you have like the complex numbers in both sets and write your bijection here. If you switch that out for like a different field, would this bijection still hold, or is this something about the complex numbers?
No, it would definitely, no. So, right, the thing is that GLNC, right, this is a complex Lie group. So its topology is like totally incompatible with the topology here. But if I change this to something like GLNQP, all of a sudden the number of maps just is going to get very much different. Like, because these things will have some kind of topological compatibility with one another, you expect there to be way more homomorphisms from a group like this into GLNQP, into something like GLNC.
Question. So that field extension E, is that every field extension, every finite field extension of QP?
No, this is a fixed. So once you give me a pi,
Right.
there's an E pi, which is a fixed extension that depends on pi.
So how would that correspond to a homomorphism from QP bar over QP to GLNC?
Right, because QP bar, right, there's a restriction map. If I have an element in here, I can restrict it to E. And right, I mean, okay, if you give me an irreducible representation, suppose I could associate a continuous homomorphism like this.
Right.
Then the kernel of that will be, right, by Galois theory, that will be like gal QP over E for some, finite Galois extension E. And the homomorphism will factor across gal QP bar over QP divided by gal QP bar over E, which is gal E over QP. So you use some infinite Galois theory to determine that these two are the same. But yeah, I didn't really want to spell out the infinite Galois theory.
Right, but per representation, you get a finite field extension, and on that finite field extension, this map is injective. But when you extend it to the whole thing, it's not necessarily injective.
That's correct. Yeah.
All right.
Perfect. Okay. So as I was saying, I want to study the wild p-local arithmetic, and I want to find some concept in representation theory which is going to let me do this. And okay, people have found it. It's called positive depth. And so it turns out that positive depth representations will give wild extensions, but you have to assume that P divides N. So we'll see an example of this, right? But this is what the correspondence looks like. So this is the kind of wild aspect of the local Langlands correspondence. It says that if you're in the situation where P divides N, then irreducible complex positive depth representations will correspond to group homomorphisms like this, where this extension E is a wild Galois extension in the sense that its degree is divisible by a high power of P. So what I'm going to do is I'm going to define this concept for you and then hopefully give you an example. Okay, but to do that, we need to say a little bit about GLNQP. And let's go to a slightly more familiar setting, so GLNR. We're claiming GLNR, you can talk about these things called maximal compact subgroups. So these are subgroups which are maximal with the property of being compact, right? And you can ask, okay, how many conjugacy classes of such subgroups are there, right? If I consider maximal compact subgroups up to conjugacy, can I count the number of conjugacy classes? And often this is an interesting question. In the case of GLNR, the answer is yes. There's exactly one conjugacy class, and it's represented by the orthogonal group. So this is the, the group of matrices which map orthonormal bases to orthonormal bases. The situation over QP is more interesting. So this is the theorem of Bruja. It says that there are exactly n conjugacy classes of maximal compact subgroups in GLNQP. And in fact, there's like a canonical way of representing them. So let me write these n conjugacy classes as K0 through Kn-1. And the statement is that there's a unique set of representatives for these conjugacy classes containing this thing called the Iwahari subgroup. So to say what the Iwahari is, I should really tell you what ZP is. So right, we saw that QP is like power series in P where you allow for finitely many negative terms, right? So you have a power series, there are coefficients and there are P's, and you have powers on the P's, and you can have finitely many negative powers of P. If your thing only has non-negative powers of P, that means it's a p-adic integer. So the p-adic integers form a subring of QP, and you can think of them just as the set of power series in P under the usual operations of power series multiplication. So what is the Iwahari? Well, this thing is going to be a subgroup of GLNZP, and it's going to be the subgroup of matrices which are of this form. So on the upper diagonal, you have just any elements in ZP. And then on the lower diagonal, you have things in PZP. So elements of ZP which are divisible by P. If you like, these are p-adic integers where the power series starts with I equals 1. So you're talking about the subgroup of GLNZP of matrices which look like this and whose inverse also looks like this. This is the Iwahari subgroup. So we'll see plenty of this subgroup in future, but the statement is that if you're interested in representing the n conjugacy classes of maximal compact subgroups in GLNQP, then you can find a unique system of representatives for those conjugacy classes such that each of the Ks contains I. And so I'm not going to actually tell you what these Ks are. I'll just give you an example. So if we take the example of n is equal to 3, there are going to be 3 conjugacy classes of maximal compact subgroups in GL3QP. And here are representatives for them. So the first one is just the subgroup GL3ZP. It turns out that this thing is always maximal and compact. And then there are 2 other subgroups, this group K1 and K2. And they're subgroups of matrices of this form. So here I allow for, I'm allowed to have something like an entry in P inverse ZP in these 2 spots, and then I have to have P ZPs down here, and then everything else needs to be in ZP. So matrices of this form, such that their inverse is also of this form, right? And similarly over here. So, so we have some compact subgroups, and we're going to use these to define a special class of subgroup in GLNQP called para-Horic subgroups. So what are para-Horic subgroups? So again, I'm going to write K0 through Kn-1 to denote these representatives for the conjugacy classes of maximal compact subgroups containing this Iwahari thing. And then we have a definition. So we say that a subgroup P inside GLNQP is para-Horic if there's some non-empty subset of the set 0 through n-1 such that P is conjugate to an intersection of this form. So it's something that is conjugate to an intersection of the maximal compacts. And here are 3 examples of para-Horic subgroups. So it turns out that the maximal compact subgroup GLNZP. So GLNZP is always a maximal compact subgroup in GLNQP. And therefore it's always para-Horic, right? Because I can just take I to be the singleton set, or theta rather to be the singleton. a nice thing is that also the Iwahari is always parahoric. So it turns out that if you intersect all the maximal compacts, or all of these representatives, K0 through Kn-1, then you actually recover the Iwahari subgroup. So that's kind of not particularly easy to prove or anything, but it is true. So the Iwahari is an example of one of these things, right? You just take theta to be the entire set, 0 through n-1. And then here's just some random example of a parahoric, right? I just intersected these subgroups K1 and K2 from the previous slide. And right, I found that the thing I ended up with looked like this. So this is also going to be a parahoric subgroup, right? So there are things which are conjugate to intersections of the Ks. And these parahoric subgroups are going to give us another example of a wild P structure. So what I will say is that these things have somehow a canonical filtration. So there's this thing called the Moy-Prasad filtration, which is basically saying that you can find some descending sequence of normal subgroups of any parahoric subgroup P with the property, so there's some kind of canonical way of choosing this P0 through P1 through P2. And I will show you examples of this. What I will point out is that these things are so-called pro-P groups. So if you don't know what a pro-P group is, that's okay. You can just think of it as it's kind of like a P group, but it's like an infinite P group. So it's kind of like a group that has order a power of P, but it's actually an infinite group. So let's see some examples of this filtration. So what I will say is that there's a way of mapping ZP to Z mod P to the I Z. So what you do is you just take your power series, you chop off the first I-1 terms, and then you reduce that thing mod P to the IZ. So that gives you a homomorphism like this. And consequently, you get a homomorphism like this. So what you can do is you can consider the kernels. I can take the kernel of the map from GLN-ZP to GLN-Z mod P to the IZ. That will give me some subgroup of GLN-ZP, and I'll get a filtration like this. So this is the Moy-Prasad filtration on this group GLN-ZP. But there are more interesting things you can do. So for example, if you take the Iwahari, we can write down the Moy-Prasad filtration. It's going to get a little complicated, but this is what it looks like. So you can ask, okay, this should be an I1. What's the first term in the filtration? So what you do is you take the Iwahari and you replace the ZPs on the diagonal with 1 plus P ZPs. Okay, so that gives you a subgroup of I1. And then the next step, what you do is you take these simple kind of subgroups here. So these entries up here and then this one down here, and you add another factor of P to them. Okay, so that's going to give you a normal subgroup of I1. And then the next step, you do it again, but this time you add P's up here. So you go from having a PZP to a P squared ZP, and then you have a PZP, it becomes a P squared ZP, and then there's a PZP here, whereas before there was only a ZP there. And then this wave of P's goes up again, and it hits the diagonal, and you get a 1 plus P ZP goes to a 1 plus P squared ZP, and so on. So, right, we get this kind of, mess of P's. What I'm trying to convey here is that this Iwahari has kind of a wild internal P structure. So, right, this doesn't have any precise meaning, but you could just kind of look at the formula here. You can see that in each of these matrices, each entry has 2 P's in it, right? So there's a PK, P. So that means that there are 18 P's per matrix. And then I have 3 matrices. So that makes 3 times 18. That's 54 P's, right? So I have 54 P's occurring in one formula here. This is a lot of P's, right? And it's an indication that we've reached kind of, we've found the P structure, right? Okay, so, right, I said that I wanted to define this concept of positive depth for you. So here we go. So what is positive depth? So if you give me, okay, so I have this word smooth here. Let's just ignore that for the, I'll quit. But about DLNQ presentations, positive depth, if it has the following property. So the condition is if you give me some parahoric subgroup of GLN-ZP, then you can consider the space of P1 fixed vectors. So remember, P1 is going to be the first term in this filtration of the parahoric that I wrote down. So what does the P1 fixed vectors look like? It just looks like the set of V and V such that if P is in P1, then pi P of V is equal to V. So the condition is that if you give me a parahoric and I consider this subspace of P1 fixed vectors, then it's trivial. And if that is true of every parahoric subgroup, then we say the representation has positive depth. Okay, so let's try unpack this a little bit. Right, so we have this smoothness thing. I should really tell you what this is. This is a topological condition on the representation. So GLNQP actually has a topology. And to say the representation is smooth is just to say that the stabilizers of all the vectors in the representation are open subgroups. So if you give me a vector in the representation and I think about the subgroup which is stabilizing it, that should be open if the thing is going to be smooth. So what this smoothness guarantees is that if you give me some parahoric P, I can always kind of go far enough into the filtration to get to the point where it will have non-trivial vectors under that filtered piece of the parahoric. So somehow, once you know the representation is smooth, you always know that you can find non-trivial fixed vectors. But the question is, how far into the filtration do you have to go? So, right, is it always possible to find non-trivial fixed vectors at the first step of the filtration? Or do you legitimately need to actually go deeper into the filtration to produce these fixed vectors? So the idea is that if you always have to go deeper into the filtration, then you say that the thing has positive depth. Okay, and I should just remark that, right, I never really defined what P1 is, right, because I didn't actually tell you what this Moivre-Prasad filtration is, but you can define P1 in kind of a slick way. It's called the pro-unipotent radical of P. It's just the maximal, normal, proper pro-P subgroup. If you know what that means, great. But otherwise, it's just some subgroup, and we've seen some examples of it. And right, I'm going to write down an example of one of these positive depth representations. So I'm going to do it for the Iwahari. So here's my Iwahari subgroup. And this thing has a filtration, right? So this is the first term in the filtration, right? I have 1 plus P ZPs on the diagonal. And then the next term, I have P squared ZP coming in the bottom right. And I get a P ZP up here and a P ZP here. So what I'll do is I'll fix a character of FP. And I'm going to define a character of this first term in the filtration. So this will be called chi psi, and it's given by the following formula. So if you give me a matrix in I1, it's going to look like this, where all these A's, B's, and C's are in ZP. And the value of this character chi psi on such a matrix is just psi of the sum of this entry with this entry with this entry, but you have to consider the sum mod P. Right, so this sum here is some p-adic integer. I can take it mod P, and I can plug it into this character psi, and that gives me a complex number. So in doing so, I've defined a character of this subgroup I1. Okay, and so I have some comments here, which are meant to give you some way of thinking about this. I think they're rather technical, so I might skip this. What I will say here is that this chi psi thing, the way I've defined it, it's actually trivial on the next piece of the filtration, right? So this subgroup I2 is contained in I1. And if you stare at this formula, right, if this matrix belongs to I2, then that means that B12, B23, and C31 are all divisible by P, right? Because I have P ZPs here. Now I have a P squared ZP up here. So when I take this sum and consider it modular P, I'm going to get 0, right? So this character will be trivial on I2, which means that it's going to factor across this quotient. And this quotient has quite an interesting structure, but I'm going to omit it here. Maybe you can ask me about it at some point. But so far we just have this character, and we're going to associate a representation to it. So what I'll do is I'll extend chi to the center times I1. So don't worry about this. The center of GLNQP is just the scalar matrices, but we can kind of delete this sentence. It's not such a big deal. And what I can do is I can form something called a compact induction. So what I'm going to do is I'm going to take this character, which lives on the subgroup I1, and I'm going to produce a representation of the entire group, right? And there's a recipe for doing this. It's not too complicated. But the statement is that this recipe will produce for me something which is irreducible and of positive depth. So what that means is that, okay, the representation is irreducible. The positive depthness is expressed by the fact that, right, if you take a parahoric subgroup and you look at the fixed vectors under the first term in the filtration, that's going to be trivial. But you can actually show that this has non-trivial vectors under this subgroup I2. So non-trivial fixed vectors rather. Okay, so what is the compact induction? Well, okay, so this is some function space on the group. So the vectors in this representation are functions from GLL3QP into C with this transformation property. So if you give me some x in GL3QP and you give me a k in I1, then fkx should be equal to chi psi of k, so that's a complex number, times f of x. Okay, and also you ask that the function be compactly supported modulo zi. And then this vector space here, right, it's a vector space under pointwise addition of functions. It has an action of GL3QP by right translations. This is just a formula for telling you how to act, but I'm going to move on here. I want to get through some of the, I want to kind of bring this together a little bit. So remember we saw, the important point is that I have this representation pi psi, yeah. Okay, so I have some pi psi, it's a positive depth representation of GL3QP, right? And I have a Langlands correspondence for GL3QP. So that tells me that this irreducible representation should somehow correspond to a group homomorphism out of some Galois group of an extension of QP. So let me fix a prime. And for each prime, I'm going to fix a character psi p from fp into c cross. Okay, and I've constructed this representation pi psi p. Right, this is a GL3QP representation. It has an associated Langlands parameter, which is a homomorphism out of some Galois group, where here E psi p will be an extension of QP, and the target is GL3C. So for each prime and for each character of FP, I'm getting a subgroup of GL3C, right? Because all these maps, right, are actually landing inside GL3C. So what I'm going to do is I'm going to define a subgroup of GL3C, which will just be the image of this homomorphism. Okay. And so you ask yourself, okay, well, you said there's some Langlands correspondence. You should be able to tell me what this image is. And we can actually kind of give you rather explicit understanding of it. So in the case when P is not equal to 3, the image turns out to have order 3 times the order of P mod 3. That's always less than 6. And you can actually say what the field is. It's just the splitting field of x cubed minus P. Okay, but something very interesting happens when P is equal to 3. So if you take the case of P equals 3, the order of the image blows up on you. It becomes 3 cubed times 4, which is 108. And this field extension becomes unknown. So we don't actually know what the extension is in this case, but we have some good information on the image of the homomorphism. So I'll just briefly kind of tell you a little bit about the image. This is my second last slide. So it turns out that the image of the homomorphism has a normal subgroup of order 27. So this is going to be the unique 3 silo subgroup inside this image. And right, this subgroup is isomorphic to some very interesting 3 group. So this is the Heisenberg group. So it's the subgroup of GL3F3 where you have, right, you just have unipotent upper triangular matrices in GL3F3. So this is a non-abelian 3 group of order 27. And I claim that it's isomorphic to a normal subgroup of this thing. And moreover, this thing has exactly 2 irreducible representations, which are both of dimension 3. So, right, at some point I gave a talk where I kind of explained this very last sentence. But the idea is that these 2 irreducible representations somehow naturally correspond to the 2 possible choices of psi3, right? So there are 2 possible homomorphisms from F3 into C cross, right? They're just the 2 non-trivial third roots of unity. Okay, and so we've kind of come full circle here, right? So I said I was going to give you some example to illustrate the schematic. So the example in p-adic arithmetic, right, of a interesting example of a field extension of Q3, right? This field E psi 3 should correspond to some degree 108 polynomial over Q3, right? And this is related to some interesting subgroup in GL3C. So these groups G psi 3, right? They're interesting subgroups of GL3C. And right, the thing that is doing the relating is this representation pi psi 3. Okay, so I'm going to end here. I have one last slide. This is the last slide. Yeah. Okay. And also there are some references, but yeah.
Let's thank the speaker. That was great. All right, do we have any questions for the speaker?
Yeah, this might be a bit more technical, but why would every homomorphism that's continuous from a profinite group to like GLNC have an open kernel? Because that's what you claimed on the slide about the finite field extensions corresponding to continuous homomorphisms.
I think it has a closed kernel, right?
Right. Yeah. I don't know. This is very technical. I'm just curious if you knew it.
But I don't know if the kernel, I mean, certainly the kernel will be closed.
Right.
That's just, it's just a pre-image of the identity, right? Which is a closed subgroup of GL3C. But I don't understand when did I claim that it was open?
Oh, yeah, you didn't claim it was open, but you said if we could go back to the ZFT version of the local Langlands correspondence thingy. So you say equivalently, every irreducible representation of GLN QP naturally parameterizes a continuous homomorphism from gal QP bar over QP to GLNC. But in the line above that, you say it's embeddings of gal E mod QP, E over QP into GLNC. So basically, this gal E over QP is actually the quotient of this continuous homomorphism by the kernel.
That's correct, yeah.
Right, but so now if you have a continuous homomorphism, you want to show that the kernel is open, because the kernel being open will give you that the quotients of finite group, and the finite quotients of this would just correspond to finite field extensions.
Yeah, so yeah, it should be an open subgroup. I think, right, you can take just an open neighborhood of the identity in GLNC, which contains no subgroups. So think about just the case of GL1C. So if you think about C cross, right, you just take the identity in C cross and draw a little dotted circle around it, right? And that region has no subgroups inside of it, except for the trivial subgroup. I claim that the same thing happens in GLNC. So the kernel is actually the pre-image of a little open neighborhood of the identity.
Right.
Which means that it's an open subgroup.
Yeah.
Okay.
Thanks.
Awesome. Anything else? All right, let us thank the speaker once again. Okay, I'm going to stop recording now.